2 weeks ago we started experiment 7. We're going to finish experiment 7 this week. Quiz number 7, anything from experiment 7 I have been told is fair game. So I'm giving you that warning, that anything from the experiment can be on your quiz this week, as well as safety is always fair game. Your rewrite of your conclusion for experiment 3 is due in lab this week, so make sure you have that ready to go when you come to lab. And then each week, make sure you're cleaning your glassware, your work area really well each week, so you don't show up the next week with dirty glassware and then can't really do the experiment. I know a lot of people with part A of experiment 7 needed or wanted new round bottom flasks because theirs were dirty because they hadn't been cleaned previously when they used them previously. So make sure all your glassware is clean and dry. We're going to talk about that, especially for experiment 8 here in a minute. So next week, we will be doing experiment 8. Make sure you read the experiment carefully. It's another week like when we used nutmeg and extracted trimyristin and myristic acid, except for it gets a little more exciting because things are more flammable and can be more exciting. So we want to follow instructions very carefully and not have that happen, because usually that means loss of experiment, so that's not good. So I'm going to talk here in a minute about glassware. The other thing is, this week in lab for experiment 8, you're going to get a half sheet of paper with a reaction on it. You need that reaction to write your pre-lab for next week. That is the specific reaction you're going to carry out in lab next week. So make sure you get that half sheet of paper from your lab prof. And then also next week, experiment 6 report is due. And a kind of side announcement, if there's anyone who's going to the medical missions conference and has a Thursday lab, see me after lab lecture today. So glassware for experiment 8. This is the glassware that you need to have clean and dry this week. So this week in lab, clean it and last rinse it with acetone and make sure it is dry. Next week you won't be able to clean or dry anything. What you got is what you got, okay? So you need your 3-neck round bottom flask. Make sure you don't have any smooth joints on any of this. You have ground glass joints, no smooth joints. If you have questions, ask your TA or lab prof. In your 3-neck round bottom flask, which can be a 500 or 250. So if your neighbor's looks different than yours, it's okay, as long as it's your 3-neck flask. You need your 1-inch stir bar in there, clean and dry as well. Liebig condenser, so the wider condenser, not the skinny condenser. You want it clean and dry, and you want the jacket dry. No wet jackets will go in the oven next week. So you won't be able to dry it next week if it has a wet jacket. And remember from experiment 4 how you dried that out. Your separatory funnel will need to go in the oven, but we don't want to put the Teflon pieces in the oven because they will melt. So make sure when you clean your separatory funnel, I take those pieces off and put them together in your drawer, but make sure you're not putting them in the oven next week. And then you need both glass stoppers, okay? So all of this glassware this week in lab, as you do experiment 7 or at the end of experiment 7, make sure you have it clean and dry. You've got a long reflux for the 3rd reaction of experiment 7, so that would be a good time to get all of this together, okay? And then we will talk about this experiment 8 next week. Okay, but make sure you get your half sheet of paper as well. So experiment 7, we're going to do step 2 of the 3-step sequence. And so we have our bromoethylbenzene from 2 weeks ago, and sometimes it's kind of questionable what state that will be in. So we're going to take our bromoethylbenzene. Make sure you note what it looks like. It may look different than it did when you left it 2 weeks ago, okay? May look darker, maybe not as transparent as it was 2 weeks ago. We're going to take the bromoethylbenzene and we're going to react it with quinoline to make the styrene, okay? And offhand, what type of elimination reaction is this? Do you know offhand what it is? Is it E1 or E2? Any thoughts? No thoughts? It's an E2. And so what does that mean if it's an E2? We haven't gotten there? No? Okay. They're all slower in lecture this semester. Okay, so it is an E2 mechanism. You will get there very soon because it's going to be on your third test, I can guarantee you. What that means, so a preview of E1 and E2, is when it's an E2 mechanism, it doesn't go through an intermediate. Okay, so you don't have an intermediate with this reaction. So you can say it's an E2 elimination, or it's a beta elimination, or it's a 1,2 elimination. It's also known, the type of reaction that it is, it's a dehydrohalogenation. So you're going to lose a hydrogen, and you're going to lose your halogen in the process. So in doing that, you protonate your quinoline, so you'll end up with quinoline protonated, and then you'll have a bromide salt off of there too. So the bromide quinolinium salt is what you're going to form from this. All right. Now we have to use quinoline. It is the base for the reaction, and we're kind of limited in our choices of what we can use. So it is a good non-nucleophilic base, and we'll talk here in a minute about why we need that. And so it's not going to form a nucleophile like sodium hydroxide, potassium hydroxide, okay? Another example of a nucleophilic base would be pyridine. So this is what pyridine looks like. Just one ring instead of two. The only problem with pyridine is its boiling point is about 115 degrees. And we need something where the boiling point is greater than 160 degrees. Okay? And so that's why we've chosen quinoline. Quinoline's boiling point is about 237 degrees. And so the reason for this magic number of 160 is that is how high we need to take the temperature before we stop the reaction. So we need something that's going to hold together up to 160 degrees and not boil away on us before we reach that temperature. And that's the top temperature where we'll be distilling our styrene off. Okay. Now the reason that we have to have a non-nucleophilic base, so we can't have sodium hydroxide, we can't have potassium hydroxide, is because where our halogen is. So we've got this halogen in our nice benzylic position. Well, instead of doing an elimination reaction, we could also do a substitution reaction. So KOH or NaOH, have that nucleophile that could do a substitution reaction instead. And so we don't want that. We want all elimination. And so for this reaction, you're going to be doing this reaction in your all-in-one simple distillation apparatus, okay? And so you'll have your bromoethyl benzene from 2 weeks ago. You'll have your quinoline in there. You're going to heat up the reaction in the heating mantle, okay? And you're going to do a fractional distillation, a small size fractional distillation. And your lower boiling fraction is going to be your hexane that may have been left from a couple weeks ago. So remember, its boiling point is about 68 to 70 degrees C. So at about that temperature, you will have hexane coming over. You want to isolate that hexane, and the reason for that is, remember, you took the volume and the mass measurement of your bromolethylbenzene. You can subtract the volume of the hexane that you've collected from the volume of your product and then figure out how much of that product yield was just hexane, so you can calculate an accurate yield for your 1 bromolethylbenzene, okay? So you need to know what this volume is of the hexane. So you can subtract that from your yield that you have from a couple weeks ago and know how much hexane is left. Then we're going to have our styrene, and it's going to boil somewhere between 120 and 160 degrees. And so it tells you in your lab manual to collect anything that distills over between 120 and 160 as styrene. Okay, so that's kind of a broad boiling point range, but about in that range is where the styrene is going to come over. All right. You don't want anything above 160, so you're going to stop the distillation at 160. All right. If you did go above it, your starting material boils about 200 degrees Celsius. Okay, so we don't want any of our bromolethylbenzene going in with our styrene. So we're going to stop at this point. You will be getting, you will collect whatever styrene that you get from your distillation, and then you will get about 1 milliliter of styrene from your lab prof too. And so we're going to help you guys out because your bromoethylbenzene may not have survived so well over the last couple weeks. So we're going to give you a little bit of styrene for the last reaction to help supplement things, okay? But you need to keep track of the styrene. So you need to know how much styrene you have and you will be using in the third reaction, and you need to know how much styrene your lab prof gave you and how much from the third reaction came from them, okay? You also need a total amount of styrene so you can calculate your yield, okay? So good bookkeeping here with your mass of your styrene. Keep track of the styrene mass and know how much you have and how much you got from your lab prof. Now, at the end of this reaction, we've got kind of, you'll have like this brown-black muck in your distillation flask, and a lot of that comes from the quinoline. The quinoline to start out with is kind of brown-black, okay? But in there is going to be the quinolinium salts, there's going to be some polymers that have formed, there's going to be all sorts of muck in this flask. If you let that cool down to room temperature, you will never be able to clean it up. It will just form this film on the glass and you won't be able to get it out. So what you need to do is cool your apparatus down just to the point that you can handle it with your hot pad, and then you want to transfer the contents of it into your waste container, okay? And then you're going to rinse the contents of it very carefully with toluene. So when you're ready to do this, have the toluene in your hood ready to go. So dispose of the contents into the waste container, and then rinse some toluene into your all-in-one simple distillation apparatus, pour that into the waste container. From there, then you should be able to clean up your apparatus, okay? But if you let everything cool in this whole process, it's not going to happen. So you have to let it cool just to where you can handle it and then start the cleanup. Now be careful with the toluene. You're going to have room temperature toluene going in hot glassware. So be careful. Keep things at the back of the hood. Don't let it splatter on you. Also be careful with the reaction itself. Don't have it splatter all over the hood either, because just like it won't come out of the round bottom flat or the all-in-one simple distillation apparatus, it doesn't come off the back of the hood very well either. Okay? So be really careful handling it. Carefully get it into your organic waste. Carefully get it rinsed out and cleaned up. Right? And everything from that cleanup goes into your organic waste container. And with all of this, you're using your hot pad. Make sure you wear gloves too. That's an extra layer there in case something did splatter. It doesn't burn you and get on you. All right? So then you're going to take your styrene on And we don't want it to sit around for too long because the styrene itself is really reactive. So once you've got things cleaned up such that you can continue on, you want to get things set up for your polymerization reaction, okay? And so in this reaction, we're going to start with our AIBN, or our 2,2' azobis isobutyryl nitrile. So I gave you that whole long name at the start of last lab period, or pre-lab period. So our AIBN is a radical initiator. It's just like our benzoyl peroxide was on step 1, okay? And so our AIBN with heat is going to form 2 radicals and then also give off nitrogen gas. So you may see a little bit of bubbling when you set up this reaction, and that is beyond just it refluxing, is probably the nitrogen gas that's being given off. So the AIBN itself, a radical, is going to react with styrene. It is going to form a radical, and what position is that radical formed in? Got a theme here. Benzylic position, right? So it's not formed on the terminal carbon, it's formed in the benzylic position. And then that radical is going to keep reacting with more styrene and more styrene and more styrene to make our polymer, okay? So our polymer is going to be this chain of a bunch of styrene units put together with one piece of AIBN on the very end of it, all right? So this AIBN starts your polymer chain. So we don't use very much of it. We don't want a lot of AIBN in there, because what will happen? If we have a lot of AIBN, what will we have a lot of?
Small chains.
Polymer chains, right? And then they'll be really small, and we won't be able to actually isolate them, okay? So we use a very small amount. You're going to use 30 milligrams of AIBN, so tiny, tiny amount. So that's, remember, 0.030 grams, not very much at all of AIBN. And just like with the benzoyl peroxide, we need to be careful with it. It nicely forms radicals, but it also can be explosive as well. So we've got to be careful handling the AIBN just like we were with the benzoyl peroxide. So we use our small amount of AIBN, form our polymer in the reaction, okay? And this reaction is carried out in toluene as well. So you've got toluene that you're rinsing out your apparatus with from the step 2, and then you're also going to use toluene as your solvent for this reaction, okay? Now one thing I forgot to cover with the step 2 reaction is our quinoline is our base. What else is our quinoline for that reaction?
The solvent?
It's the solvent, yep. So for step 2, your solvent is the quinoline. It's also your non-nucleophilic base. For step 3, we've got our styrene, our radical initiator, our AIBN, and then our solvent is our toluene, okay? And so our polystyrene is very soluble in the toluene. So we need to do something to get it out, all right? And so what we are going to use is what's called a selective precipitation. So with polystyrene, our small chain polymer is soluble in methanol. Our large chain polymer is not soluble in methanol. And so we are going to cool down our reaction mixture from this reaction. And you want it cooled to room temperature, okay? And then you're going to have a beaker full of, I believe it's 150 milliliters of methanol, so a decent amount of methanol. And you're going to have it rapidly stirring, okay? So this is at room temperature, methanol is at room temperature, your round bottom flask is at room temperature. So let it cool down completely from the reflux. Then you're going to slowly add your toluene mixture to that methanol, and you should get your polymer crashing out, okay? At least the large chains of your polymer, okay? So this, hence, if you use too much AIBN, you're not really going to get anything to crash out. So make sure you use the correct amount of AIBN. You're going to very slowly add the toluene while it's stirring, keep everything stirring. And what you want is you'll eventually see a white precipitate forming, and it should look kind of flaky. You don't want anything that looks like globs or kind of stringy or anything like that, because what that means is it has the toluene trapped around the polystyrene and the methanol can't get to it to help it precipitate out, okay? So you want solid that's flaky, not globs of stuff that is stirring around. So the slow addition of the mixture to the methanol is important to make that happen. So make sure you add your mixture slowly, okay? And then it gives you a stir time. You're going to let it stir in the methanol, and then you're going to filter it with vacuum filtration, and then you will have your polystyrene, okay? Now remember with step 3, so we talked about last week for your pre-lab, steps 1 and 2 you're going to calculate. In your pre-lab you should have calculated traditional theoretical yields, and you'll calculate traditional theoretical yields and percent yields after you've completed the reaction. So step 1, step 2, regular yield calculations. Step 3, remember, we have to calculate a weight percent yield for step 3. And so you're going to, once you isolate your polystyrene, you're going to take your grams of polystyrene and you're going to divide it by all of the styrene, so the total of your styrene and the styrene you get from your lab prof. And that is how you're going to figure out your weight percent yield for polystyrene. So remember, for polystyrene, it's a little bit different calculation, okay? Now, just like we did for step 1, where we had some characterization of our product. So step 1, remember, we did the relative density of our product in ethylbenzene in water and compared that, and then also did the silver nitrate test. That was your characterization test for your bromoethylbenzene. That's how you confirmed that you had made it. For part 2, your characterization test is going to be the boiling point of the styrene, okay? So what boiling point range that your styrene distills over at, as long as it's in the 120 to 160 degree temperature range, then it can be identified as styrene. For part 3, you're going to collect the IR spectrum of your product. And if you look in experiment 5, where the instructions are for collecting an IR spectrum of something, there are instructions for a liquid and instructions for a solid. So this time we're going to have a solid sample, not a liquid sample. So make sure you follow the instructions in experiment 5 for collecting them, okay? So you'll have your IR spectrum. Now, one thing you have to be careful with this IR spectrum is sometimes you have to let your polystyrene dry a day or 2 because that methanol doesn't completely dry off. So if you have time in lab, try collecting the IR. If you've got a big OH peak in your IR polystyrene, then you probably still have some methanol left and you need to let it dry a little, okay? The other thing that we use for characterization is what's called GPC, or gel permeation chromatography. So I'm going to talk to you about that and let you know what our modification for this year is for the gel permeation chromatography. Okay, so do make sure you have your IR spectrum, and make sure you have the yields of all 3 steps, as well as the characterization of all of the steps that you need. Okay, and then I'll talk to you in a little bit about what we're going to do for GPC. So. First of all, any questions on procedure yet? Okay, so let's talk about the technique known as gel permeation chromatography. The word chromatography is going to become very familiar to you over the next few weeks, because we're going to use chromatography this week. We'll analyze experiment 8 with a type of chromatography, experiment 11 with chromatography, and experiment 12 with chromatography, and experiment 14 with chromatography. Okay? So many opportunities to become familiar. So this type of chromatography, gel permeation, chromatography, abbreviated as GPC. It's also known as SEC, which is size exclusion chromatography. With each type of chromatography, you will always have a mobile phase and a stationary phase with the chromatography. Okay? So I'm going to give you what those are right now for gel permeation chromatography, and then we'll talk about how that works for this type of technique. So our stationary phase is this polymer gel that is on the column that we're going to use. So we've got this very, very thin column, and there's a polymer gel that's inside that column. And this polymer gel isn't just one chain of polymers, but it's also cross-linked. So if you remember from last week when we talked about cross-linking to give it a little bit more strength, this is an example of that. So we've got the stationary phase, it's this polymer gel. Our mobile phase is the solvent or the eluent that pushes everything through this column. So when you're talking chromatography, your solvent is always referred to as your eluent. So what we have with this column and this polymer that's attached to this column is inside the column is we've got like these, the gel itself kind of forms all these nooks and crannies. So it's not just smooth gel without any porousness. It's got all these places where things can travel, okay? And so you'll have your sample plus your solvent traveling through, and then it'll come out the column and then be detected on the other end, okay? Well, large samples don't travel through there so well, okay? So bigger things can't fit in there as well. They can't fit in all of the nooks and crannies. Smaller molecules can fit in there. so with the smaller molecules, because it can fit in between all those spaces and as it travels through the column, it's going to go through as many of these as possible, or sample all those nooks and crannies as it goes through. So smaller molecules take longer to get out of the column because they can fit in all those spaces and travel through all those spaces as they go through the column. Larger molecules can't fit in all those spaces, so they take less time to come out of the column, okay? So larger molecules elute first, or come off column first. Smaller molecules elute later. Okay, so this is important for understanding how things are separated. And so you can separate based on size using gel permeation chromatography. Just how the size discriminates how it can fit through the column itself. Okay? And so what you do is, first of all, when you get a GPC result, you kind of will see big blobs of the larger molecules, and then you may see more definite peaks of smaller molecules at the end if you had true definite peaks to see. Okay, so the blobs come off first, and then the more definite peaks would come off later. To figure out what things are and what they weigh, what their molecular mass is. So if we look at a GPC, this is kind of a drawing. It's also in your lab manual of it. We've got solvent, goes through a pump. We have our sample is injected through the injector, and then it goes coming from the sample tray into the injector, goes to the column oven. So that's where the column is in this column oven. And then it's detected, and then once it's detected, the computer interface tells you what is detected. So we know what things are. We'll use, we make a calibration curve. So we use standards of known molecular weights to standardize the instrument, and that way we can figure out then from other samples what molecular weights are present, okay? So when you have things of known molecular weight, of one specific molecular weight coming off of the GPC, you will get definite peaks. You won't get the big blobs, you'll get definite peaks, okay? In a minute, I'm going to tell you about the polydispersity index, but the polydispersity index of these compounds is 1, okay? So just keep that in mind here a little bit. So we have this calibration curve, and then what happens is we've got this polymer that has all different molecular weights present, okay? We haven't done anything with your polymer to make it of a specific molecular weight. We haven't controlled anything in the formation of the polymer. So you've got this sample that has a lot of different chain lengths and a lot of different molecular weights. And so you get this polymer of all these different molecular weights, a lot of this one, few of this one, so forth. And so your curve in the end ends up looking like this blob, okay? Well, then what we can calculate are average molecular weights. We can't really calculate specific molecular weights in this blob, but we can calculate what the averages are that are present, okay? And so that's what you would get from your sample, is you're not going to see a specific peak. You're going to see a blob from your sample and then figure out what molecular weights are present. And so the two things that we use for molecular weight, we define molecular weight with two different calculations. And so one is probably going to be very familiar to you, and another one you may not have seen before. familiar way is just to use a simple mean. And it's the same simple mean that you have calculated for many years in all of your math classes and other classes. So it's just an number average molecular weight, and it's signified by Mn, and it counts all polymer strands equally. The second way to calculate it is what's called a weighted average. And this is signified by MW. And in this average, the bigger polymer strands are counted more. And so if you look at this transparency, what it's shown here for this sample is the Mn, if it was calculated for this sample, is going to fall right in here, versus the Mw would be more towards the larger strands of the calculation, okay? And so with this, it's also showing you where that average is going to be. So this is a figure from your lab manual, and so that's what it's showing you in that figure. An example, instead of just looking at that graph, an example of how this is actually calculated. Let's say we have, and this is the example from your lab manual too, if we have a football team and we're looking at the different weights of the football players. So on this team, we have one player that weighs 150, two players 180, one player that's 210 pounds, and two players that are 250 pounds, okay? And so if we calculate Mn based on this, we just add up all those weights. So we take 150 plus 180 plus 180 plus 210 plus 250 plus 250 divided by 6, and we come up with 203. Or another way of looking at this is it's equal to 1/6 times 150 plus 1/6 times 180 times 1/6 times 180 plus 1/6 times 210 plus 1/6 times 250 plus 1/6 times 250. So in all this, everything is weighted the same. And again, we'll come up with 203. If we look at using MW, then what we do is we're taking into account what that weight is for that specific number. Okay, so if we add up all these weights, it's 120. And what we're looking at is the ratio of the weight over that total. So we'll have 150 divided by 1220 times 150 plus 180 divided by 1220 times 180 plus again 180 divided by 1220 times 180 plus 210 divided by 1220 times 210 plus 250 divided by 1220 times 250 plus 250 divided by 1220 times 250. If we go through all of that math, we come out with this average being 210 instead of 203. Okay? So the MW is always going to be at least as large as MN, and a lot of times it's going to be greater than MN. Okay? And so what we use to describe the relationship between MN and MW, so if we wrote MN, we wrote the ratio of MW over MN, we would get what is called the polydispersity index. Which is also known as the PDI. And so if you had that equal to 1, you would say that your polymer is monodisperse. Okay? The only way for MW over MN to be 1 is for them to be the same, and the only way for that to happen is for everything to weigh the same. Okay? So you would only have one size, one molecular weight polymer chain in that sample. Usually you've got it greater than 1. And so if your PDI is greater than 1, then that is polydisperse. Okay, so your sample is polydisperse. And so usually for the experiment that you guys are doing, the sample is usually about 2, has a PDI between 2 and 30. Okay. So for looking at GPC information, 3 pieces of information that you want, so this information is going to be calculated for you, is you need to know MW, you need to know MN, and you need to know PDI for that sample. Okay? And so I told you that we're going to do things a little bit different this year with the GPC. So the GPC is kind of a cranky instrument, and each year it takes a little bit to make it happy. Usually its pump is what is unhappy. And so this year, Dr. Sanford got it started again, so this instrument is one of Dr. Sanford's for her research group. And she got it started, and the pump works like a charm. It's very happy, it doesn't leak, it's doing what it's supposed to. So she tried the autosampler. Well, the autosampler is not happy, and so we can't put samples in if we don't have a way to do that, okay? And so our GPC is not working so well. So what you are going to get is you will have GPC data to analyze. It just won't be GPC data of your particular sample, okay? But you will have GPC data from previous years of people making their polystyrene and what their GPC data was that they analyzed, okay? So included in your report for this experiment, and remember the experiment 7 report is the 75-pointer report, so you want to do a really good job on it. You're going to want to analyze the MW, the MN, and the PDI for that sample information that you're given from your lab prop this week. Okay, so make sure there's a lot of other information on there. These are the 3 values that you want off of there, and then you need to analyze what that means for that particular sample. and how that would potentially relate to, if it were your sample, how would that relate to your sample, okay? Now you do still, so you'll have GPC data just given to you, but don't forget, so we won't be making any GPC samples. Don't forget, you do want the IR spectrum of your product, and you need your yields. Remember, you're going to need yields calculated for all 3 steps, and then the other characterization that I talked about for the other steps too, okay? So you've got 3 of the, 3 reactions that you need yields, 3 reactions that you need some form of characterization for as well, okay? Questions that you guys have? Yes?
Did you say we're doing GPC on other labs, or are we doing this?
Well, so in other labs, we're going to use other forms of chromatography. This was the only lab we're going to use gel permeation chromatography. We're going to use different forms of chromatography in the other labs. Yes, Gavin?
For the experiment 3 rewrite due tomorrow or on Thursday, depending on what lab you're in, does that go in your lab notebook, or do we just hand that in?
I would talk to your lab prof about what they want. For me, I want your notebook, and I want the conclusions slid into your notebook.
Slid in, but not put in?
Not attached yet.
Okay.
So otherwise talk to your lab prof and see what they want.